So today it's my pleasure to introduce our speaker who is not going to speak, Lucia Sbragia. Lucia has problem with her voice. So my understanding is that Michèle will step in, but Lucia will participate also here and there. Lucia is professor at Durham University Business School. She published a long series of papers in different areas, and particularly in environmental economics. She is expert in international environmental agreements, among other things. So thank you, Lucia, for accepting the invitation. And the floor is yours. I don't know who is going to start. I leave it to you.
Okay. I think I'll take over right now. And I'm going to improvise using the very nice slides that Lucia sent me a few minutes ago. And I will do my best, but this is joint work. We work together on this paper, and it's, I think, an interesting new twist to the growing literature about stability of international environmental agreements. So I will introduce, give some motivation for this well-known problem, present a model, talk about the game, present some results, and then conclude with a surprise at the end. So to introduce this topic, let's just say that climate change is something that is on the minds of many people. And we're again talking about the possibility of agreeing to do something about climate change. So what we have here is that on Geneva, the 4th April 2022, so we have just received the third part of the 6th assessment report. And it seems that the global greenhouse gas emissions are not abating, and but the rate of growth has slowed. What is everybody now is probably admitting is that we should reduce emissions if we want to reach the objective, which is to limit global warming to 1.5 degrees. What is also true is that it is possible to do so, but it requires a lot of let's say commitment and reduction probably in consumption and things like that. So what is also on the table is that if we want to do that, we have to start now. So this is to introduce this paper. As we say in these in this environment, climate change is a global problem. We need global solutions, and environmental agreements, they require voluntary participation, because there's nobody who can force countries to participate in these agreements. So what you have here is a short history of cooperation on climate change, and the last one, COP17 in 2011, and where participating countries agreed to adopt a legal agreement on climate change. Okay, and we have the last one in Paris, COP21, where 195 nations signed the Paris Agreement, and they defined some commitment that they wanted to take. And but it is a vast participation. And countries did submit pledges, but there's no punishment or way to enforce these pledges. Okay, and there is some discussion about if the pledges are enough to limit the temperature increase to 1.5 degrees C. Many experts think that the pledge are not enough. Still, it is a vast participation, and what we're going to see in our model, what we're going to discuss is an interesting question. Is it better to have a vast participation or to have large commitments? So this is, in fact, the research question that we are addressing. And we're using a model to address this question, which has different features from the usual international agreements models. The first feature is that the countries that are participating, or they agree on participating to the agreement, are not cooperating with each other on deciding on their level of emissions. Now, this is usually what is done in this literature, is to suppose that signatories or participating countries are representing a single player, that everybody is cooperating and deciding emissions jointly. In our model, we don't suppose that. We suppose that countries decide on their emissions individually. What the agreement is about is agreeing on a commitment to attain some common target. So this is what the agreement is about. And we relate this loosely to the Paris Agreement. It's not exactly the same as the Paris Agreement, but we say that in the Paris Agreement, there is a common target that was agreed by participating countries, okay? And there is also freedom of action on the way to reach this target. The second distinguishing feature of this model is that we are putting something in the utility of players that we call a self-image, that represents some assumptions about what it means to agree to a commitment. So we're supposing that the signatory countries have this self-image part in their utility function. And it's related to the fact that when a country signs this agreement, it develops a sense of responsibility towards the commitment. And this self-image is a kind of the way they look at themselves about if they did attain the target or not. Is it adds or subtract to their utility. For example, when a signatory country does not respect its commitment, there's a sense of shame, which is a kind of negative utility. And when the signatory country overcomplies with the common target, then there's a sense of pride, which adds to the utility. Now, this is clearly a mechanism that helps signatory countries gain something from the fact that they are reducing their emissions. So it is also related to some existing literature. For instance, what is called naming and shaming. That is also present in the Paris Agreement, because their pledges are not binding. There are no sanctions, no punishment, but they are periodically reviewed, and countries say they disclose whether or not they did attain their pledges, or they did do what they promised. And you have this naming and shaming that appears in some literature about human rights also. And this is the negative part of the utility function. We also have this positive part that is related to the warm glow that empirically is observed when people do the right thing, or do the thing that is considered to be a good thing. And it has been observed in experimental literature. Okay, so let's go to the model. We have n symmetric countries. We have a quadratic benefit from emissions. We have quadratic damage from accumulated pollution stock and a linear evolution of the pollution stock. So this is the very classical model that you see everywhere. Maybe the only difference is that here we have two terms. One is linear and one is quadratic, which is slightly more general than the usual either linear or either quadratic model. And so this is the model for the welfare of a country. We're considering an infinite horizon problem. Pollution accumulates. This is the rate of at which pollution accumulates, and this is the total emission from all countries. Okay, and the agreement again is about attaining some common target, and there's no deadline. It's just that they should reduce their emission in order to attain this target. And we suppose here that the target is some fixed constant that has already been decided, but I will come to that at the end. You have two groups of countries. You have green countries that are parties to the IEA and brown countries, N green and M brown. And the green countries, since they have committed to to this agreement, they have a self-image component in their utility function. And we suppose that the self-image component, which is a measure of how far they are from the target, it is added to the utility with some weight, and the weight depends on the seriousness of the environmental problem. It also depends on the ambition of the pledge and clearly the degree of compliance to the agreement. So this is the self-image component. There it is. So it is some constant, some parameter lambda multiplying the difference between the target and the emission of each country. So if your emissions are lower than the target, then it's positive. If the emissions are higher than the target, it's negative. And we suppose that the weight here is the same for negative and positive parts. Okay. The self-image component is simply added to the welfare of the green countries. And what we suppose here, and this is important, is that this weight, it is proportional to the pollution stock, which represents the seriousness of the problem. It's also proportional to something that we call ambition of the pledge, meaning that you could always choose a very high target, and meaning that when you're not ambitious at all, jumping it just a little bit is not giving you much of a warm glow. So the ambition of the ambition of the pledge is this parameter alpha. More ambitious you are, the more warm glow you get, and conversely for when you're the shame. Okay, so this here, to represent the ambition, we just simply suppose that the target is some kind of reference point divided by the ambition. So the reference point could be anything. It could be some norm. It could be some, for example, emissions at 1990 emissions, things like that. In fact, the reference point is not really important because the ambition parameter is directly related to that. Okay. So we have two possibilities that are that we consider in this paper. Either this reference point is a constant, R0, or it could be a strategy that depends, that adapts to the level of the pollution. So we're considering both possibilities. Okay, so what the game is played in two stages. The first stage is the membership game, where countries decide to whether or not they're going to participate in the agreement. And the second stage is the emission game, where green and brown countries decide independently on their emission levels. And this is done at discrete dates over an infinite horizon. And I repeat that green countries do not form a coalition. They are deciding independently of each other about their emission level. We make a simplifying assumption. Countries are myopic with respect to the evolution of the size of the agreement or the number of signatories. And the terms of the agreements, that is the ambition of the pledge, or the reference points, which are in fact equivalent, are fixed. So this has been decided before. Now I'm talking about the evolution of the number of signatories. We could suppose that the number of signatories doesn't change, that is a closed agreement, or we could suppose that it changes over time. Clearly, the stability will depend on the level of pollution. So this is possible in our model. We can do both. But in any case, the countries are making their decisions about their emission without considering the possible evolution of the number of signatories. I recall that there's a paper by Samar, which considers a model where countries are not myopic with respect to the evolution of this of the number of signatories, in a model where we suppose that this is replicator dynamics. And this paper shows that there is the structure of the game is not really much changed by this assumption. Okay, so here we're starting to first solve the emission game. So we solve the emission game at a given for a given number of signatories. And well, this is pretty standard. You can show that in this linear quadratic model, if all countries are using linear strategies, the best response is linear for all the players. And so that we can find an equilibrium value function, a Nash equilibrium. And this value function is quadratic in the pollution stock and can be characterized analytically. Was there a question? I heard somebody. Yeah. So the characterization is analytical, but the solution is not in closed form because you have to solve a couple of coupled quadratic equations. But it can be solved quite easily numerically. And what we get is a result that is represented here for a given n. What you have in red here is the value that is obtained if all countries cooperated. This is the first best solution, the value function. And what you get in black here is the non-cooperative solution for that particular example, non-cooperative solution where nobody signs an agreement and everybody's acting independently. And what you see in between is the result of our model where depending on the value of parameters, you always find that the green countries can achieve something that is somewhere between the non-cooperative and cooperative solution, and the brown countries also. So you get some, here you see that this is represented as a function of the pollution stock level. And here you see that for, in that particular example, for 50 signatories, the green countries are always well, they have value that is lower than the brown countries. This means that this agreement would not be stable. Countries would leave the agreement because they would be better off leaving the agreement. Here you have a representation of what's happening with emissions. You have the target here, this dotted green line, and you see that this emissions, non-cooperative emissions, cooperative emissions that are lower than what are emitting the green countries, and also lower than what the brown countries are emitting. And you see that the brown countries are emitting somewhere that is close to the non-cooperative solution. So, but the average in yellow, this is the average of all countries, this average achieves something that is better than the non-cooperative solution. Okay, but still, in that example, it's not a stable agreement. The question is, can we make it stable? So we solved the membership game. The membership game is solved using the non-cooperative point of view, where we assume that an agreement is stable if it satisfies the internal and external stability conditions. And recall that this is done in a dynamic framework. So we have to check if an agreement is stable at some given pollution stock. Okay, so this is the generalization of the internal and external stability conditions for a dynamic problem where we suppose that at some given pollution stock, green countries, if the value of green countries at N is better than what they would get, what the brown country would get if the green country would withdraw from the agreement, then this is internally stable. And on the other hand, if brown countries at P and N, if they are better off than if they would join the green countries at P with N+1 signatories, then this agreement is externally stable. So these are the conditions that we're checking to see if we can obtain a stable agreement at some P. Now, in the results that I will present here, we always look for the stability of the agreement at the steady state. Now, this is we could look at the stability at any P, but we did all the computations at the steady state. And in any case, we check that the form of the results is robust to the choice of the pollution stock. Okay. So what we're going to look at these are numerical results. We're going to first answer a question, can this setting where we don't have cooperating countries, can it generate stable agreements of meaningful size? As everybody here knows probably, the puzzle of the small coalition is the fact that we cannot, in the general setting, we cannot have agreements that have more than 2 or 3 players because of the common good or common bad feature of the pollution stock. So we're going to answer this question. I'm telling you right now, yes, we can have a stable agreement. And then we're going to look at these agreements and see what happens with when we're moving some parameters of the agreement. For example, what is the relationship between the ambition of the pledge? Recall that we say that this pledge is fixed. It's decided in advance. So what about moving the ambition of the pledge? Does it change a stable agreement, and does it change the welfare of countries? And does it change the pollution stock? So we're going to look at that. And we also look at the relationship between the concern parameter, gamma, which is the weight that is given to this self-image in the utility function. So we call this the concern parameter. This is something that could be increased by, for example, doing more publicity or information about the consequences of climate change. And we see that if some countries get more concerned about the problem, this parameter measures how important the self-image becomes with respect to the revenue part or welfare part of the utility function. Okay, so this parameter alpha is related to the agreement itself. Parameter gamma is related to information, education, that could change over time also. So we have here some results that I will show you. Here you have a base case here where all our numerical results were we're using a base case that we chose that to be representative of a reasonable solution. We're doing all the sensitivity analysis inside an assumption that we have parameters that are reasonable in the sense that the cooperative solution and non-cooperative solution both are positive. Okay, so this is where we're doing our analysis. So here we have one example where you have here internal stability, external stability, and we see that there is a stable agreement right here somewhere around 54 countries, where with these parameter values, this would be stable at the steady state. Okay, so here this ambition parameter is computed by choosing a target that is somewhere halfway between the cooperative and the non-cooperative solution. So if we're targeting to be somewhere between the two, this is what this agreement is about, and corresponds to an ambition here is of 0.7. So the answer is that yes, it's possible to get self-enforcing agreements when signatory countries include self-image in their utility function. Okay. We see here that at this point, you have emissions and value function, where at this stable agreement, where you see here that the value function of green and brown countries is, well, it seems to be almost the same, but in fact they're crossing somewhere around the steady state. But at the steady state, they're comparable, and they're somewhere between the non-cooperative solution and the first best solution. So you're getting an improvement here. This in yellow is a total welfare, not including the self-image component. So you see that there's an increase in the total welfare, even if we're not considering the self-image component. Recall that this black line and this red line here are the value functions of in the non-cooperative case and the cooperative case without a self-image component. So in this yellow part here is the part where we're just considering the welfare itself. So we see that this setup, in fact, can generate interesting solutions. What you get here is the same representations for emissions. Here you have a constant target. This is the first best, and this is what the green countries are doing. This is what the brown countries are doing, and what you get the emission is somewhere between the non-cooperative and cooperative solution, and this means that we have a reduction in pollution also. What I'm presenting here is some sensitivity analysis about the parameter values. So the first one is the ambition parameter. Again, ambition is how high is your commitment. So clearly, if you say that you're going to reach emission level that is very low, that is a very ambitious one, this is going to be costlier. And what happens is that the number of signatories at stability, the number of stable signatories is decreasing with the ambition parameter. Okay, so the more ambitious you are, the less people are going to sign in. Okay, and this is based on the stability condition. And this results in the fact that also you can see that the more ambitious you are, this was not obvious, but what we find is that the more ambitious you are, the higher is the pollution stock at the steady state. In other words, if you want to have a high participation and a low pollution stock at the steady state, you should choose an alpha that is relatively small, not too ambitious. Okay, so what you see here is that at some point, if you decrease the ambition a lot, what happens is that you have here full participation is attained. What is not represented here, but we checked, is that after, if you still continue to decrease the ambition, you get the full participation. This stays on, but the impact on the pollution stock becomes negative, because then you get full participation but less welfare. The same here. You have the same result. This is the case for a constant target. This is the case for a state-dependent target. You get the same kind of results. As you probably notice here, the only difference is that it's much more sensitive, because here you see that the alpha varies between 68 and 74, and here it varies between 92.5 and 97.5. So you get the same kind of result, but much more sensitive to the ambition parameter. So the negative impact of ambition on the pollution, the number of signatories and pollution stock, it comes from the fact that the results, the pollution, the emissions are really driven by the number of participating countries. So this is the important result that we have here. What you see here is the impact of this alpha parameter on the emissions, the green emissions and the brown emissions. Now, you should be aware that these are different scales. So the brown countries are much less sensitive to this alpha parameter, almost not sensitive. So this is the scale for brown countries. But what you see here in that example, in all the numerical experimentation that we made, is that as you increase the ambition, the individual emission of green countries is decreasing, and also the individual emission of brown countries is decreasing. Okay, and on the other hand, if you're increasing the ambition, what happens is that even if individually emissions are decreasing, globally total emissions are increasing, because the number of participating countries is going down. Okay, so as you're increasing ambition, what happens is that the total emissions by all countries is increasing. Okay. So this is what is written here. Total emission increase due to an increasing proportion of brown countries which have a higher emission level. Okay. Now these results are robust. They are robust to different values of base case values, but they are also robust to constant or state-dependent targets. What you see here is the impact of the ambition parameter now on the welfare and utility of countries. So you see that as you're increasing the ambition parameter and you become more and more ambitious, you have a negative impact on total welfare and total utility. The difference between total welfare and total utility is the self-image portion. So you see here that, first of all, increasing the ambition is not welfare increasing, but you also see that the self-image part in this utility function is relatively, it's not that important. And we still get some interesting results. Now I move to the other parameter, the gamma parameter, which is a concern parameter that is how heavy is the, what is the weight of the self-image with respect to the revenues, welfare function. So you see here that the when the concern of countries is increasing, you have a positive impact on the number of signatories, which has a negative impact on the total pollution stock, which is something that is not surprising. And you get also here some information on how this gamma parameter impacts in individual emissions. So when gamma increases, emissions by green country decreases, but emissions by brown country increase. And this, since gamma also has an impact on the number of signatories, if you look at the total emissions, they are decreasing in gamma. So even if these are increasing, the total emissions are decreasing because the proportion of green countries is increasing with gamma. Okay. So these can be explained easily by looking at you have the impact of all these players competing for the Nash equilibrium between the two competing for the emissions, but also the fact that the number of signatories, the self-image, are pushing them to decrease their emissions. Okay. And now the last sensitivity analysis is about this welfare and utility. And again, not surprisingly, if you increase the concern parameter, countries are more concerned about climate change. It will make the self-image more important, more signatories, and it has a positive impact on total welfare and total utility. Again, this red line is the welfare part, total for signatories and non-signatories, and doesn't include the self-image portion. Okay, so to conclude this numerical experiments, when the the target depends on the current pollution stock, you get the same kind of results. Stable agreements can be achieved. Players are strategies are more sensitive to variation in the self-image parameters, but you get the same kind of results. It's just that the scale is smaller, and the sensitivity analysis of gamma is the same thing. Individual emissions are also increasing in gamma, but they are more sensitive when you have a target that depends on the current pollution stock. Okay. Now, a last thing that I want to show you, it's because all these analyses are done at the steady state. That means at the point where the number of signatories no longer changes because pollution no longer changes. So you have a stable agreement and the stock of pollution is at the steady state. The reason why we did that at the steady state is that we could argue that this is what we're going eventually, what is going eventually be reached if we had this kind of setting, and at some point we would reach this steady state where pollution is stable, number of signatories is stable, and there we have seen that the results depend on the ambition of the pledge and depend on the concern parameters, and a good result is obtained with a relatively small ambition parameter and a relatively large concern parameter. Now, what I want to show you is how this works over time. So let's suppose that we have an open membership setting. This means that at some point you have an agreement that it is stable, but as the pollution stock increases or decreases, the number of the stable number of signatories changes with the pollution stock. So how does it change over time? This is what we're going to show you. So the the setting is the following. At each decision date, countries observe the current level of pollution stock. They decide on their emission level, and depending if they are signatories or not, they're using a self-image part or not in their utility function. And then this gives you an equilibrium emission strategy, and this makes the pollution stock evolve. And at the new pollution stock, then players can revise their status, and they can decide to enter in the agreement or leave the agreement, depending on the welfare of the green or brown countries becomes larger. Okay. For the we're going to present here 3 scenarios, the 3 or 4, I don't remember. 3 scenarios about how the number of signatories is going to evolve over time. And we already know how pollution evolves, but how does the number of signatories evolve over time? In the first scenario, we suppose that at each decision date, they observed after they have decided on their emission quantity, they look at the new pollution stock and then they just reshuffle so that the new agreement is stable. So the required number of countries leave or enter. So at each point of time, the number of signatories is the stable one at this pollution stock. So that corresponds to the assumption that is made in Rubio and Ulf in 2007. So at each decision date, everything is reshuffled or some move, and so that the agreement is always stable. And that means that at each decision date, previous period participation does not enter into that. You just decide how many countries are going to be in the agreement. The second possibility second scenario is a simple rule, say that if the greens are better off than the brown ones, then one country joins at each decision date. And if the brown ones are better off, then one country leaves the agreement. Okay, so in that case, you don't have a membership gain. It's just that at each decision date, one country leaves or enter based on the myopic vision of who's getting a better deal. But clearly, countries will reach a stable agreement by trial and error by doing that. In that case, previous participation does have an impact because you're moving from the current. And the third scenario, did you put the fourth one? No. We have 4 in the paper, but the third scenario is the evolutionary pressures that move the number of signatories depending on the relative value function with respect to the average one. So here you have the NP+1 that increases if the green are better off than the average and decreases otherwise. So this is the replicator dynamics. And I'm going to show you the results. But you see here, there are 4 on it where instead of being additive like this, it's going to be a multiplicative one, but it's still a replicator dynamics. So you have here examples of what happens over time, depending on the initial conditions. Here, they're all starting with, let's say, 20 signatories and a pollution stock of 450, and this is how it moves over time, reaching the steady state. In the first scenario, they go there directly because at each point of time, the number of signatories is stable. And the other scenarios, well, you eventually reach it more, maybe slower, at a slower pace, and you overkill some the pollution, or in some, depending on where you start, you could also overkill the number of signatories. So here is one example of the time evolution, the pollution stop. Here is another one where you present here the forces that are pushing these trajectories. So here in the dotted black line is the number of signatories corresponding, stable one corresponding to each pollution stock. And in the dashed blue one, you have the steady state pollution corresponding to each number of signatories. And clearly the steady state is when these two lines cross. And you have here trajectories depending on where you start, how you will reach this, like this one. Okay, so when you, supposing that you're here, you're over this line. So this means that you're going to reduce the number of signatories. At some point here, you cross this line, so you're going to try to increase the number, the pollution stock, and you finally reach this this steady state where we did all the numerical investigations. So this is interesting because we see that depending on the assumptions we made about how countries enter or leave agreements, we have different kinds of trajectories, possible trajectories. So let me summarize and conclude. What is interesting here is that even when signatory countries act independently, supposing that they have some self-image that is related to doing good or doing bad with respect to some commitment, it means that we can obtain quite easily stable self-enforcing agreements where the welfare, there's a meaningful size, but also these agreements are effective because they reduce global pollution, they increase global welfare with respect to the new agreement solution. We also found that there's a trade-off between ambition and participation. The more ambitious you are, less countries will enter into the agreement. And this has a clear negative impact on the economic and environmental outcomes. There's also a good relationship, fortifying relationship between awareness of the risk or like concern from the countries and the participation, meaning that it's a good idea to talk about climate change if we want people in countries and governments to be willing to do something to solve the problem. Now, what is, I think, the most important takeaway from this thing is that broad participation is better. So it's better, seemingly, to have a broad agreement that is not too ambitious, than to have a very narrow agreement that is ambitious, because the participation is the key driver to obtaining a reduced stock of pollution and overall welfare. So this is a question that has been asked, and even at the beginning of these international environmental agreement literature, is it better to have a large or small base on the agreement? It seems from in our model that small ambition, large concern is something that works well. But also what happens when you because the question that is also interesting, it's good to have a small ambition, but could you put the ambition to zero? The fact is that when you reach full participation, if you decrease the ambition further, then you have a negative impact. Total welfare starts going down and pollution starts going up again. Okay, so here I see that Lucia wrote that the further work is choice of the target. The surprise is that I solved it. So I can tell you now that I solved the third part of the game, the one where we decide what is the best target. And not surprisingly, from our results, the best target is to choose a target small enough to get full participation, but not smaller than that. So if we want to have a kind of perspective of what should be done, we should strive to have the largest participation possible. So adapt the ambition of our targets in order to be able to have as many countries possible to join the agreement. So I will stop here and let Lucia answer the questions.
Thank you, Michèle. Thank you, Lucia, for nice presentation, very nice slides.